Hey guys, so today we're going to talk about differential equations, and I'm going to be using the worksheet that you guys have access to as kind of a guideline. So first I want to tell you what a differential equation is. A differential equation is an equation, obviously, involving the derivative of a function. One of the distinguishing features of a differential equation is that whereas ordinarily solutions to equations are numbers, this next sentence here says that a solution to a differential equation is actually a function, usually denoted y, which satisfies the equation. So as I said, this is a little peculiar. In your entire mathematical career up to this point, were always numbers, like x equals 5 or x equals 7 or something. But in a differential equation, your objective is not to find an unknown number, but rather to find an unknown function. So here are a few examples with solutions. Let's consider this first differential equation here. Now, first of all, why is it a differential equation? Obviously, it's an equation because it has an equal sign. And, well, it's a differential equation because it has a derivative, right? dy dx means the derivative of y with respect to x, so that makes it a differential equation. Now, verbally, what this equation says is that the derivative of y is x squared. That's what this thing says. The derivative of y with respect to x is x squared. Well, a solution to this equation is going to be a function. The function which satisfies this differential equation is y equals 1/3 x to the third. Why does that function satisfy the differential equation? Well, just think about it. This differential equation says that dy dx, that's the derivative of y, is x squared. Well, is the derivative of this function x squared? Yeah, it is. So therefore, this function satisfies this differential equation. Again, notice that the solution is not a number, but a function. Let's have a look at this second differential equation. This equation says that the derivative of y is actually itself, right? The derivative of y with respect to x is y. A solution is y equals e to the x. Because if you recall, the derivative of e to the x is actually itself, e to the x. So does this function satisfy this differential equation? Yeah, because if we look, is the derivative of y with respect to x y itself? Well, yes, it is. Okay, and then maybe just one more here. dy dx is equal to 3y. This equation says the derivative of y is 3 times itself. A solution is y equals e to the 3x. And, you know, if you want to check that, just have a look at what dy dx actually is, right? dy dx would be, well, we sort of have to think of the chain rule, right? This function here, if you want to differentiate it, the outside function is e to the blank, right? So the chain rule says we take the derivative of the outside function. The derivative of e to the blank is just itself. What goes inside the blank? Well, the original inside function. Done, we have to multiply by the derivative of the inside function, and the derivative of 3x is just 3. So we see that dy dx is 3 e to the x, but this thing right here, e to the 3x, is in fact y. So this is actually equal to 3y. So you can see that this function here has the property that its derivative is 3 times itself, and therefore satisfies this equation. We've already seen a bit of this, but let's just make it clear. A lot of times in AP problems, you'll be asked to verify or check that a certain function is a solution to a differential equation. It's pretty easy to do that. You pretty much need to just plug it in. Let's consider the differential equation y double prime is equal to negative 4y. This is saying that the second derivative of y is equal to negative 4 times itself. What function has that property? I claim that the function y equals sine of 2x is a solution. Now, how would you check that? How would you check that this is a solution to the equation? The same way that you would check any other proposed solution to any other equation. If someone gives you an equation and they say, I claim that x equals 5 is a solution, how do you check that? Well, you plug x equals 5 into the equation and you make sure that it's actually true. You can do the same thing here. Okay, so to check that this function here is a solution to this differential equation, we have to verify that it satisfies this differential equation. We have to check, in other words, that the second derivative of this function is negative 4 times the original function. So let's compute the second derivative of y. The first derivative of y because the chain rule gives us 2 cosine 2x, and then differentiating a second time gives us negative 4 sine 2x. And this quantity right here, that's y, right? So we see that y double prime is equal to negative 4 times y, the original function. So it's clear, therefore, that it satisfies the original differential equation. Now here's a really important point. Differential equations by themselves have infinitely many solutions. Let's consider the differential equation dy dx equals y. We saw this a minute ago. In words, this equation says the derivative of y is itself. Certainly the function y equals e to the x is a solution since the derivative of this function is itself. But actually there are other solutions. For instance, y equals 3 e to the x is also its own derivative. If you differentiate this thing, you get the same thing back. So this function also satisfies this equation. And also y equals 4 e to the x is also a solution. And in fact, in general, any function of the form y equals c e to the x, where c is any constant, is also a solution. Therefore, rather than having a single solution, we actually have a family of solutions, one solution for every choice of c. Now, I want to emphasize that this is typical. It's nothing to do with this particular differential equation. Generally speaking, differential equations by themselves have infinitely many solutions. Now, the solutions tend to be all related, like they all have a certain form, but there do tend to be infinitely many. However, if someone gives you not only a differential equation like this, but an additional piece of information called an initial condition, then that additional piece of information, the initial condition, will uniquely specify one and only one solution. So let's go through this. Often a differential equation comes with additional information called an initial condition. Let's consider again the differential equation dy dx equals y. We know there are infinitely many solutions. We just saw a bunch of them up here, right? 4 e to the x, 5 e to the x. There are infinitely many solutions to that guy. But let us suppose that we are given the initial condition y of 0 equals 4. That means that when x is 0, y is 4. In other words, when y is evaluated at 0, you get 4. This additional information will narrow the solutions down to a single unique solution. Well, let's see why. We know from what we just sort of did up here that y equals c e to the x is the form that the solutions to this equation have, right? They all have that form, y equals some constant c e to the x, y equals 3 to the x, or y equals 4 to e to the x, 5 e to the x. They all have that form. But if we now apply the initial condition, we'll see that a unique solution is specified. So the initial condition again says that when x is 0, y is 4. So if we take this equation here and we replace x with 0 and y with 4, we obtain this equation right here. Now e to the 0 is 1, and so that whole right-hand side is just c. And we find that 4 is actually equal to c. Which means that, look, without the initial condition, c represented an arbitrary constant. It could be any value you wanted, 3, 4, 5, negative 12, doesn't matter. But the initial condition forces c to have the value 4. This means that we have a single unique solution, namely the function y equals 4e to the x. Okay. Now some terminology. The original solution, the general solution, y equals c to the x, this is called the general solution to the differential equation, all right? This formula here really represents, as we saw, an infinite number of different solutions, all of which have this same form, right? One different solution for every possible choice of c. So this formula, this general solution, represents the total solution set, all possible solutions to the differential equation. But the unique particular solution that we obtain by applying the particular solution, okay? So if you're not given an initial condition and you're just given the differential equation, then you can only find the general solution. It will involve at least one arbitrary constant like c. But if you're given an initial condition, you'll be able to find the value of that arbitrary constant, meaning that you'll actually have a specific unique solution to the problem. So let's move on to see how we actually solve differential equations. So, you know, we only learn one technique for solving differential equations in this class, and it's called separation of variables. I'll outline the steps here, but you'll see what I mean when I actually do the example. So the first thing that you should do is always use Leibniz notation. If you remember, that means writing dy dx instead of y prime. So switch to dy dx instead of y prime if it's not already in that form. Now what you do is you pretend that dy dx is literally a fraction. This is one of these weird cases where, you know, technically dy dx is not actually literally a fraction, but we sort of sometimes pretend that it is. This is one of those times. Use algebra to get everything involving y on one side of the equation and everything involving x on the other side. Okay, this step is called separating variables. So you've got two variables, y and x, and what you're going to do is put everything involving y on one side of the equation and everything involving x on the other side of the equation. That's separating variables. Then you integrate both sides of the equation, and when you integrate, remember your constant of integration c. Okay, I make this little note here. I say you only need one constant of integration even though you're doing two integrals. The reason for this is complicated, but for now just take my word for it. Step 4, if you have an initial condition, use it to find your arbitrary constant c. Remember that, you know, with an initial condition, c will actually be forced to take on a particular value. So after you're done integrating, you should use your initial condition to find the value of c. If you don't have an initial condition, then you just have to leave c as it is. Finally, you solve for y in terms of x. So that's an outline of the process, but let's see how it actually works in practice. Example, solve y prime equals root y over x squared with the initial condition y of 2 equals 9. So let's follow the steps. So first of all, we should replace y prime with dy dx, right? We should use Leibniz notation. The next step is to separate variables. That means we're going to get all the stuff involving y on one side, all the stuff involving x on the other. You can think of this in a few different ways. I guess you could think of it as cross multiplication or something. From this line to this line, what I'm doing is I'm multiplying both sides by dx. Again, pretending that that the left-hand side is literally a fraction. So I multiply both sides by dx and I obtain this line here. Now, if you'll notice, I've still got, you know, all of the stuff involving x is on the right-hand side, and that's good. But I need all of the stuff involving y to be on the other side. And this root y here is annoyingly still on the right-hand side. I need to move it over to the left-hand side. And the way to do that is to divide both sides by root y. So I divide both sides by root y, and I obtain this line right here. Notice that everything involving y is on one side, everything involving x is on the other. So now the variables are separated. So that's step 2, okay? Now that the variables are separated, you're going to integrate both sides of the equation. So I'm just going to slap an integral in front of both sides of the equation. On the left-hand side, we're integrating with respect to y. Y is the variable. You can see the dy there. The dy is telling you that you're integrating with respect to y. And over here, you can see because of the dx, you're integrating with respect to dx. Now the left-hand side, I don't really care for this dy floating around in the numerator. I find it a bit confusing. It's better, I think, to rewrite dy over root y as simply 1 over root y dy, and I think it makes it a bit more clear exactly what function you're integrating if you write it in that form. So if you want to find antiderivatives of these functions, remember that's what the integration is doing, right? This is an indefinite integral. It simply means find the antiderivative of each of these functions. So in order to find the antiderivative, it's best to rewrite each of these functions using negative or fractional exponents as needed. 1 over root y really is just y to the negative 1/2, and 1 over x squared really is just x to the negative 2. So I'm now ready to find some antiderivatives for each of these two functions. Antiderivative of y to the negative 2 is 2y to the positive 1/2. And antiderivative for x to the negative 2 is negative x to the negative 1. And notice that I've put the plus c here. That's the constant of integration that you obtain whenever you're computing an indefinite integral. In other words, an integral without limits of integration. You might be tempted to put like a plus c or something on both sides of the equation, as I mentioned before. You should not do this. You should only put a c on one side. The reason for this, like I said, is kind of subtle, but for now, just take my word for it. Put a c only on one side. Now, if we didn't have an initial condition, then there would be no way to determine the value of c. C would have to be left as an unknown constant, but because we have an initial condition, we can plug that initial condition in and find the value of c. So what was our initial condition? It was this thing here, y of 2 is equal to 9. That's saying that when x is 2, y is 9. All we have to do is go to our equation here and replace x with 2 and y with 9, and then that brings us here. And if you notice, c is the only unknown in the equation, which means we can solve for c. If you simplify everything, 9 to the 1/2, that's root 9, which is 3. So 2 times 3 is 6. And then this thing here, 2 to the negative 1 is really 1/2. So, this whole term here is negative 1/2. So we find that 6 is negative 1/2 plus c. Adding 1/2 to both sides, we find that c is 6.5 or 6.5. So now that you've found the value of c, you can go back to where we were before we plugged in the initial condition. That's this line right here. This is where we were before we plugged in the initial condition. Go back to this line, and now that we know what c is, now that we know that c is 6.5, you can replace c with 6.5. So go ahead and do that, and that brings us here. The only thing left to do is to solve for y. Remember that what you're trying to do is to find the unknown function, y, which satisfies the differential equation. Therefore, y is actually the unknown that we're interested in here. So we should isolate the y. Fractional and negative exponents are good for differentiating and integrating, but I find that when it comes time to actually solve equations and isolate variables, fractional and negative exponents are a little confusing, and so I prefer to switch back to, a more conventional notation before doing the solving. So rewriting these terms gets you here, right? Y to the 1/2 is root y. X to the negative 1 is 1 over x. Now, we want to solve this thing for y. Well, we have to get the y by itself. So you should begin by dividing both sides by 2. All terms get divided by 2, right? So the negative 1 over x becomes negative 1 over 2x, and the 6.5 divided by 2 is 3.25. Finally, to isolate the y, we square both sides. So the whole right-hand side gets squared, and we obtain this expression. And this is a function, right? This quantity here, y equals negative 1 over 2x plus 3.25 quantity squared, that is a function. And it is a function which is guaranteed to satisfy this differential equation. If you wanted to check it, and it would be kind of a pain to do so, but you could check this by, first of all, computing y prime. Find the derivative of this function and replace the left-hand side here with whatever you find. Second of all, take the square root of your function, which I guess would just get rid of the 2, and then divide by x squared, and check and see if those two sides are equal. You'll find that they are. I won't go through it, but you'll find that they are. So this is the function which satisfies the differential equation. This is the solution to the differential equation. Okay. So here are the exercises that I've asked you to do, and I think I'm going to do number 1 with you, and then you'll have enough experience to go on your own. So consider the differential equation dy dx equals 2x over 3y squared. Part A says use the method of separation of variables to find its general solution. I really want to emphasize general solution. Remember what that means. If you don't have an initial condition, then all you can find is the so-called general solution. Remember, in the first example we looked at, that was y equals c e to the x. You're going to have a function y involving an arbitrary constant c, an unknown constant c. That's the general solution. It represents an infinite family of solutions. So because we don't have an initial condition yet, the general solution is the only thing we can actually find. So let's go ahead and do that. So the first move is to, well, first of all, convert to Leibniz notation if we have to. We don't have to here. It's already in Leibniz notation. So what I'm going to proceed to do is separate the variables. I put all of the terms involving y on one side and all of the terms involving x on the other. You can think of it as cross multiplication or however you want to think of it. If I multiply both sides of this equation by 3y squared, getting rid of this denominator here, I get 3y squared dy over dx equals 2x. Okay, so if I multiply both sides by 3y squared, that's what I obtain. Now I can bring the dx over to the right-hand side by multiplying both sides by dx. So I'll go ahead and do that. I obtain 3y squared dy equals 2x dx. Now, at this stage, you should notice that I've separated the variables. All the terms involving y are on one side, all the terms involving x are on the other side. The next step, if you remember, is to integrate. I integrate both sides of the equation. So I'm going to integrate the left-hand side with respect to y, and I'm going to integrate the right-hand side with respect to x. So of course I have to find antiderivatives of each of these functions. The antiderivative of 3y squared is just y to the third. And an antiderivative of 2x is just x squared. Now we have to remember our arbitrary constant of integration, plus c. And again, you should only use one of them. It's typically easiest to put it on the side involving x, although it doesn't really matter, but just one constant of integration. Now, if we had an initial condition, then I would plug that initial condition in right here, right now. But because I don't have one, there's nothing to plug in, and the only thing left to do is to solve for y. So, of course, to do that, I just take the cube root of both sides. In other words, I raise both sides to the 1/3. So if I raise both sides to the 1/3 power, or in other words, take the cube root of both sides, this is what I obtain. And that is my general solution. And understand that this is really an infinite family of different functions. One for every choice of c, one function for every possible real value choice for c. Okay? And no matter what c is, any function of this form will satisfy this differential equation. So that's the general solution. Now, in the next part, I give you a initial condition, y of 0 equals 2. I'm telling you that when x is 0, y is 2. That is going to pin down the value of c. It's going to determine uniquely a value of c. So let's see how that works. You can choose to plug in 0 for x and 2 for y in this equation, or you could choose to plug it into this equation. It doesn't really matter. Either way, you're going to have to isolate c. But I will say, though, that generally speaking, it is typically easiest to plug the initial condition in to the equation that you obtain immediately after integration. That's this one right here. Okay, you can use this one, but it requires more untangling typically. So I advise you that when you have an initial condition, use it the moment that you're done integrating, the moment that your arbitrary constant c appears. So let's go ahead and plug 0 in for x and 2 in for y into this equation here. So I'm going to obtain, I'm replacing y with 2, so I have 2 to the third is equal to, and I'm replacing x with 0, so that's 0 squared plus c. Well, of course, 2 to the third is 8, and then 0 squared plus c is just c. So I find that c is equal to 8. So you see that this initial condition forced c to take on the value of 8. Which means that I no longer have this infinite family of solutions, the general solution. I actually now have a particular solution, the one particular solution which satisfies not just the differential equation, but also the initial condition. And that's this one right here. This is my particular solution, okay, which satisfies the differential equation in general, yes, but also satisfies the initial condition here. Part C. Find the particular solution that passes through 3, -2. This is just another way of saying that you should find the particular solution satisfying the initial condition y of 3 equals -2. So all this is going to do is it's going to give you a different particular solution. It's going to give you a different value for c. Now, if you go back to, say, this equation right here, and you replace x with 3 and y with -2, you'll obtain, let's see, so replacing y with -2, I have -2 to the third is equal to x, which is 3 quantity squared plus c. So I'm just plugging the initial condition into this equation here. If I do that, as you'll see, I get a different value for c. -2 to the third is -8. 3 squared is 9, plus c, subtracting 9, looks like I get negative 17 equals c. So that gives me a different value for c, which gives me a different particular solution. So I have, instead of x squared plus 8 to the 1/3, replacing c with the value I found, negative 17 in this case, I have y is equal to x squared minus 17 to the 1/3. And that's the different particular solution here, okay? All right, so I think that is it for today. This equation here, you may have some kind of difficulty getting the variables to be separated. It causes confusion to students sometimes because there's a y only on the right-hand side. There's no x on the right-hand side. You can still just multiply both sides by dx if you like. That'll give you dy is equal to negative y squared dx. And then divide both sides by negative y squared. And that'll give you negative 1 over y squared dy equals dx. So now the variables are separated. And then you're probably, I'm doing a little bit more of this problem than I planned to, but at this point you integrate, right? So you're taking the integral of negative 1 over y squared dy, and you're integrating on the right-hand side just dx. A lot of students will look at this thing and they'll say, what in the world is that? What am I integrating? If there's nothing there, it's really like a 1 dx. You're integrating 1. And so what is the antiderivative of plain old 1? Well, it's actually x, right? The left-hand side, I think the antiderivative would be, let's see, I think y to the negative 1, wouldn't it? Yeah, that's right. Equals x plus c, okay? Because the antiderivative of 1 is x. So, okay, so that would be, the first moves for number 2. Okay, good luck and have fun.